I will introduce Kate Larson. She is a professor and holds a university research chair in the Cheriton School of Computer Science, University of Waterloo. And Kate is also a research scientist with Google DeepMind. She is an AAAI Fellow, AAAI Fellow, and her work has been awarded several Best Paper awards, including at the International Conference on Autonomous Agents and Multi-Agent Systems, also known as AAMAS, and ACM Conference on Computer-Supported Cooperative Work and Social Computing. Because she likes seeing cooperation in action, she has been involved in organizing and supporting many conferences and workshops in different roles, including at AAMAS as General Chair and IJCAI, IJCAI as Program Chair. So, yeah, please, Kate.
So I think the lesson there is that our field has way too many acronyms. I remember going to some actually quite technical seminars at the University of Nelson as a grad student and having no idea what was going on simply because it was just all acronyms and I was making up my own matching. It was just a disaster. Okay, so welcome. I was asked when I was invited, I think Cecilia gave me some ideas about what I might want to talk about. And she said, you know what, you've done quite a lot of work on cooperative game theory and coalitions and teams. And so that might be a topic that you could talk about. So I said, okay, I love coalitions, I love cooperation, I like seeing it in action. But I also am at heart have an interest in sort of in principled methods. So I like having formal foundations that we can build upon. So what I'm going to talk to you about today is something called cooperative game theory. So to give you one particular framework for reasoning about groups. I also thought I wanted to do sort of an introduction to cooperative game theory because I'm sure that a lot of you are familiar with non-cooperative game theory, concepts around like Nash equilibrium and strategies. But cooperative game theory is not as well known, and I think it will provide hopefully some insights or at least questions that might be useful as we think about sort of cooperative AI as a research agenda. So I'm going to organize this very much as an introductory lecture because I know some of you already know all this material. So Ben's my former PhD student. I hope Ben knows a little bit about this. So he never actually worked in cooperative game theory. There's a few other of you in the room I know have a bit of background. So just bear with me. But I'm sure for the rest of you, it might be sort of quite new. So I'm going to, at a very high level, talk about what is a cooperative game. In particular, there's a particular formalism that we'll be talking about, which is very, very general. I'll then say, okay, if we have a cooperative game, how do we analyze it? In particular, in cooperative game theory, there's a variety of different questions that we can ask, but the two predominant ones are stability. Is our cooperative structure stable or is it going to fall apart? As well as fairness. Are we somehow sharing the benefits of cooperation in a way that, from the outside at least, looks fair? So we're looking at some very kind of classic examples of what we mean by stability and what we mean by fairness. And then after that, I'm going to sort of go beyond the basics and, again, at a very, very high level, sort of highlight 3 different research papers or problems that have been looked at. 2 of them are from my own work, but one of them is not. It's just an interesting model that I keep on coming back to, and I keep on seeing examples where I think it would be a useful way of framing the problem. If I have time, I'd then like to break you up into small group discussions so you can sort of chat among them yourselves, because that's kind of fun, and then before concluding with questions. Now, I only have an hour, so I don't know whether we will get into the small group discussion part or the questions, but I'll sort of do my best. Don't hesitate to ask me questions as I go along, so you don't need to wait to the end. I believe Cecilia said that there's a way of posting questions online that she can feed to me. But also, if you have a question or a comment, just feel free to interrupt me. I quite like kind of dynamic audiences. I kind of thrive off the energy a bit. Okay. So a little bit of an introduction. When we talk about cooperative game theory, we're talking about something very specific. So I'm going to use the term cooperative game theory and coalitional game theory interchangeably. And what this is sort of a branch of game theory where the focus is no longer on the individual per se, it's going to be on the group. Okay? So these groups are going to be, of course, formed by individual agents. And these individual agents we're going to make the assumption that they're self-interested, so they might have their own sort of incentives or utility functions or preferences which are driving their behavior, but we're not going to be so much interested in that. We're going to be interested in sort of what cooperative structures will emerge in the context. So in particular, we're going to be given a set of agents, okay, again, potentially self-interested, not necessarily adversarial, but just self-interested. And then we'll talk about a coalitional game. It's going to define kind of how each group or coalition, again, so a coalition is simply a group of agents or a subgroup of agents, how well those groups, when they coordinate, are going to be able to do for themselves. And so the questions that we'll ask are, well, what groups should form? Okay. Particularly, maybe if we have some outside the system optimizers trying to coordinate everybody into little sets and into the tables and so on. A good question to ask is, well, what would form a good way of forming groups? But also we allow agents to have autonomy. So the other question that we could ask is, well, what groups will form? In particular, if we're trying to arrange people in this room, we want you all sitting down. We don't want you switching from one table to another table, otherwise we would never be able to listen to my lecture. And then finally, we can ask, okay, once a group of agents have formed a group, well, there's some benefit for being in that group. So how should that be shared among the members? And there's different objectives. You might want to make sure that you're sharing the benefits of belonging to a group sort of equally. You want it to be fair. I mean, of course, equality is always complicated because what does it mean to be equal? What does it mean to be fair? Cooperative game theory gives some suggestions as to what that might mean. But also you might want to ensure that the benefits among the group are also sort of stabilizing the group so that we don't have this, this unstable system. So those are the basic questions that cooperative game theory likes to look at. Okay. Now, as I said, I'm going to do sort of very, very basic introduction, just to give you some language so that you can look at some of the literature in this space and it's a little bit more approachable. But I do want to make a note that these ideas from cooperative game theory, some of the ideas that I'm going to mention, are actually quite widespread, particularly across sort of the social choice and the economics literature. So they're going to be very, very closely related to ideas that we see in bargaining, we see in voting, as well as in market equilibria and so on. So some of the terminology you might have encountered before. Okay. So definition. We're going to be looking at coalitional games with transferable utility, so TU games. And I'll talk about what that TU means in a second and why we're making this assumption. So it's going to be defined by a pair. So in particular, we're going to have a set of agents. We're going to have N agents. Again, these are self-interested agents, right? We're going to put no particular constraints on them. But the second bit is going to be interesting. The second bit's a function, which is a characteristic function. So a characteristic function is simply going to be a mapping from the power set, the agents. So in particular, what it's going to do is going to sort of, given a set or subset of agents, it's going to retain what we call the payoff or the value of that set of agents. Okay? And we will, because we are going to be working this transferable utility setting, we have this transferable utility assumption, we're going to assume that if a subset of agents can achieve some particular value, somehow, it depends on the context, then those agents can share that value among themselves in any way that they might want. So they're able to transfer this utility or credit or payoff amongst the members of the group. Okay. We will also make the assumption, is for simplicity form, that the value of no agents, so the empty set, is going to be 0. But that's the only restriction that we will, for now, put on these characteristic functions. Okay, so what this can capture is sort of complementarities between agents, substitutes among agents, but there can also be disadvantages of having particular agents in a particular group, and the characteristic function would be able to capture that with assigning negative value to some particular groups. Now, just because I've already pointed out that we are looking at the class of transferable utility games, so that is an assumption about what we can do with a value of group. There's another group of games called the non-transferable utility games. There you also, it's defined in a similar way. Again, you're going to have a characteristic function, but you no longer necessarily have that possibility of transferring value between the agents in the group. Instead, it becomes a little bit more complicated. There's still ways of sort of sharing credit among the members of the group, but they're going to have different preferences and so on. The basic ideas that I'm going to cover today will also apply to the non-transferable utility setting, but it comes with significant notational overhead. So that's why I'm just flagging it that these other games exist and they might be appropriate for sort of applications that you're interested in, but they are slightly more complicated when we're reasoning about them. Okay. So now let's ground this definition with a couple of examples, which I have two running examples. So the first is a classic voting game. The idea is that we have some government made up of different parties. So we have 4 political parties, A, B, C, D. They have 45, 25, 15, and 15 representatives each. And they want to pass a spending bill. Say, I don't know, $100 billion spending bill. But you need a majority in order for this bill to pass. Okay? So you need at least 51 votes. Okay? Now, what's interesting here is that no single party here has enough votes in order to pass the bill. There's no party that holds a majority. And so these parties will have to form groups or will have to form coalitions in order to pass this bill or not. Okay? We will assume then if the parties decide, if the spending bill is passed, well, then the parties get to decide how to allocate what projects get what money, so how to allocate that money in the spending bill across our different priorities. If the bill's not passed, then everyone will get 0. So this is clearly a cooperative game. It can be modeled using coalitional game theory. Again, our set of agents will just be all the members of the parties. We're going to assume that those representatives are heavily aligned to those parties, so they're not going to break off and vote differently. If party A says, this is what we do, then that party is being, the representatives are being whipped, if you're in the Canadian or UK context. We're going to have a characteristic function. The characteristic function just assigns a value for each subset. So in particular, the characteristic function of some subset of the parties S will be 100 billion. 100 billion. If the size of the coalition is more than 51, has more than 51 representatives in it, 0 otherwise. Another little example will be in a classic kind of resource sharing game. Again, I'll use this as my second running example. The idea is that we have N adventurers. They're searching for gold and silver, and they come across some pile of treasure in the woods that has more than 2 times N bars. Now, these bars are going to be really heavy, and so it requires like 2 adventurers to work together in order to carry out a single bar. So again, this is a cooperative game because groups of agents have to work together in order to carry these gold bars out of the forest. So our game will be the set of agents, so our N agents. Our characteristic function is simply going to be how many bars would a particular group be able to carry out, right? So in particular, you need a pair, so it's going to be the size of the group divided by 2 and then the floor of that because you need 2 people to carry out a bar. Does anyone have any questions about the basic model? Yes?
In the mapping from the subsets to the reals, don't you need that? The intuition is that the utility is transferable. Yeah. So if I have subset A and subset B, shouldn't their utilities individually be equal to like the utility of A and B?
Not necessarily. So in some cases, yes. Some cases you are going to have Your characteristic function might be super additive or could which is really quite nice. It makes sort of solving these games interesting. But you can sometimes, but it doesn't have to be the case. There are going to be situations where there are sort of diminishing returns as you add more agents or people into your group. And so you'd like to have your, your characteristic function capturing that. In particular, if you have a situation where you want to model, for example, the communication cost, at some point the communication overhead might be too large to make it worthwhile to have more agents sort of added to the group. It will depend very much on the context that you find yourself in, what modeling assumptions you want to make.
So just as a follow-up to that then, that's how I understood transferable. So what is transferable actually referring to?
The transferable simply means that, well, we're going to have some examples of solution concepts are going to rely on this transferable utility thing. But what it really means is that the group gets, or the subgroup of agents gets some value. And then inside the subgroup, they can take that value and then split it up among themselves however they want. Okay. Any other questions? So what I've done is I've introduced this really basic idea of a cooperative game. But we want to be able to analyze them, because what's the point of having a model if you can't use it to understand something? And so a lot of the analysis of cooperative games is going to look at how, okay, we formed a group, or maybe a bunch of groups. There's some value achieved by belonging to these groups, or what these groups can, generated by what these groups can accomplish together. How do we divide this among the agents themselves? So again, this becomes the transferable utility problem. You can think of this as sort of payoff or money or utility. It could also be credit, right? Agents have some credit. The group gets some credit, and then we do sort of a credit assignment internally. So what we will assume is that we can transfer utility or these payoffs, these values, kind of between the members of our group. And we're going to capture that by payoff vectors, or formally called imputations. It's simply going to be some vector x, which says, well, what value does each member, either in the group, get? Okay. Now, there's a few constraints that we are going to put on our set of imputations. Typically, what we'll have is a feasibility constraint, which says if I have a coalition, in this case, I'm talking about what we call the grand coalition, so all the agents are in a single group, but this also makes sense if you look at subsets. We'll have a feasibility, which says, well, you cannot allocate more between your agents than the value that actually exists from that group. There'll be an efficiency constraint typically, which says you don't want to leave any value on the table. So if a group can get some value of n, or some value, we'll say k, I want to make sure that it's distributed across all the members of that group. And then we'll also have an individual rationality constraint. So in particular, underlying assumption is that these agents are actually self-interested. They can decide whether to be a member of a group or not. So it should be in their own interest. In particular, you don't want a situation where a particular agent would be better off just working independently. So we do have an individual rationality constraint, which often comes into play.
Yeah, thanks. Can I ask about the units of x? So I'm thinking if I'm allocating money and money matters a lot more to somebody than it does to somebody else, then it's more efficient to allocate it more to the first person. And then it's like, okay, is it utility, but then it doesn't make sense to add up utility to a resource constraint?
Yeah, so that's actually, this is a model, and so of course I am on wheels. This is not good. There's details which I'm sort of brushing aside. So they might have utility. They might be interpreting kind of like the x that they get in different ways. And that I'm going to brush under the table. Right now, I'm only looking at this sort of reward division. There's something, and I'm just deciding. I'm not telling you how the agents are actually interpreting this particular x. But that's going to come in a little bit later when we talk about what sort of divisions are we actually interested in. And of course, I am going to be making the assumption, I'll be making a bunch of assumptions that sort of simplify the problem just for explanations, but when you begin applying it, you do have to worry about things like that.
Just
Yeah. Is feasibility necessary for all cooperative games, or could you have situations where smaller groups, if added up, get more utility than will drive competition?
Yeah, absolutely. So yes, okay. So I have put no structure, very little assumptions on this characteristic function. For notation reasons and just to make things a little bit easier today, I am going to be implicitly assuming that we're dividing up this grand coalition value, but that might not necessarily be the one which has the greatest value. So if we have some games that will be, so everybody working together is always going to sort of maximize sort of the characteristic function. But I think the interesting cases are when that's not the case, when there are issues around sort of scale, coordination overhead means that actually smaller groups are more interesting. You are still going to have a feasibility constraint, even if you are more interested in these smaller subgroups, because for any particular coalition, if we say, okay, this is the one that's going to be forming, we're interested in dividing up its rewards, you cannot divide more than the group actually has. So that's a good question. So we have a framework. It's quite abstract, but very flexible. Now we can kind of begin sort of analyzing it. So in particular, the question that we're going to ask is, how do we divide this value that the group or the coalition is creating amongst its members? Again, this could be money, credit, gold bars, right? Powers, lots of different kind of interpretations that we could use as to what this value actually is. But we're going to be working at the abstract level, and we're just going to say, okay, let's divide it. Okay? And in particular, there are lots of ways. An imputation just has, it's just a vector proposing kind of a division, satisfying a few of those, the feasibility, the efficiency, and the individual rationality constraint. That's still a very, very large space of possible divisions. So what we are interested in is among the set of all possible imputations or payoff vectors, which ones should we be focusing on? So in particular, which ones will we consider good? And our definition of goodness will depend on what we are actually trying to achieve. So the two common ones that we'll look at is stability. So would agents want, given a proposed imputation or payoff vector, will the agents be happy, or will they want to break away from the group and reorganize amongst themselves? So we want to understand kind of what are stable payoff vectors and which are not stable. Because the last thing we want is sort of a cooperative system where agents are where everything's in sort of chaos. There's no fixed point. Agents are switching from one group to another group. The second thing that we might be interested in is fairness. So looking inside sort of the individuals of the group, so at the system level, we might want to know, well, is this fair? Do the payoffs or these values that are being assigned or the credit that's being assigned to each individual agent, does it actually some way capture what value the agent brings to that coalition? Okay, and so what we'll do is that we'll talk about these two different ideas, and we'll look at sort of solution concepts from cooperative game theory that look at stability and look at fairness. And of course, this is going to be a situation where you can't necessarily get both. They'll be these are very different concepts. So the first thing we'll talk about is stability. And there's different ways of measuring stability, but this is sort of the most common. And the idea is called the core. Okay? So we say that our imputation or our payoff vector is in the core of some cooperative game, where a game's given our set of agents, as well as our characteristic function, if and only if this particular constraint holds. So basically, you're defining the core by laying out a set of constraints. Okay? So you can stare at it, or you can sort of do a little bit, of math, right? Sort of write down what these constraints might mean. But in particular, if this constraint holds, it means that no subgroup of agents, so no subset S, has some incentive to break away and form their own coalition. So in particular, the payoff vector is such that, so no matter what coalition that they would form, they're not going to get any benefits from breaking away. Or they won't be able to reach an agreement with some other set of agents to improve their outcome, given sort of what we have proposed to them. Okay. So again, this is this is the classic stability definition. If you have a payoff vector which is in the core, then everybody is happy to sit there. There's no way that there's no incentive for them for subsets to break away, new tables to form, so on and so forth. This is sort of as best that they can do. They're given all the other agents. So kind of the equivalent of a Nash equilibrium, roughly like a sort of a fixed point, sort of, but in the cooperative game theory space. Yes. I am making an implicit assumption. Right now I'm just talking about sort of payoffs. We'll assume sort of expected, they're expected utility maximizers. I'm not worried about models of alternative models of bounded rationality here. They could do full look ahead and so on and so forth. But I will also talk a little bit about approximations, which might be interesting if you do have sort of different types of agents in your system. Okay, but this is just sort of the most general model that we have. Okay, so let's look at some examples in the treasure game and the voting game. And we want to say, okay, well, what's in the core? So in particular, do there exist these imputations or these ways that we can allocate value across the agents so that the game is stable, right? In particular, that the game that we think that should be, the outcome that we think should be supported is actually supported, and agents are not sort of disappearing and moving between different groups. And we've sort of lost, the system somehow lost control. So in the treasure game, I'm just going to assume that I have an even number of gold bars, and it's 2 times the number of agents in my group, just to make it easier. If n is the number of agents that I have is even, well, my imputation is going to be everybody gets 1/2. Okay, and that's in the core. No subgroup of agents can break away, form their own little group, and sort of carry gold bars out and do any better. By renegotiating the deal with each other, than this particular division. If n is odd, however, the core is empty. There is no stable outcome. In particular, if we have an odd number of agents, when we carry out those gold bars, there's going to be somebody who didn't really carry out anything, and so in theory, could potentially get 0. But, right, because we don't actually, but anyway, it gets a little bit complicated. But what we can find is that we can get these little subgroups where somebody is actually willing to be paid a little bit less in order, and somebody will take a little bit more to form sort of a subgroup, and then maybe actually get some more gold bars. Okay. Again, what you do, that you set up your system of constraints, and you can show that there's nothing that can be computed there. In the voting game, and I'll leave that as an exercise to you guys to figure out what the core is in. In the voting game, remember we had 4 parties with different number of representatives, and they had to get a majority vote in order to pass a bill. Again, the core is going to be empty again. So in particular, there is no way to divide up that sort of $100 billion between the agents that wouldn't allow some subgroup to sort of break away and sort of form an agreement. Again, you sort of set up the set of constraints, and you kind of see that there's just no solution. However, if you change the problem and you say you actually don't need a majority, you have to have, I guess, a supermajority, you need at least 80 votes, then we do have something in the core, so there is a stable solution. But in particular, there's lots and lots, potentially almost an infinite number of stable solutions, because if we require 80 votes, if you go back and remember kind of the structure of our game, you have to have that party A had to be in that coalition, and party B had to be in that coalition, and all the others, the other 2 were kind of irrelevant. So in particular, what this means is that any outcome where A and B are collectively sharing the 100 billion between themselves in any way is going to be in the core. It's going to form a stable coalition. They have no way of breaking off and forming kind of a subgroup with some other agent. Okay? So now we go from having no stable outcome to having possibly an infinite number of stable outcomes. So the problem with the core is that it's very, very strict, and sometimes it's empty, and sometimes it's almost too big. Now, I can't do much about the core being too large, but it's interesting when we do have lots of elements in the core, right? It means that there's sort of lots of opportunities for cooperation among our agents. But when it's empty, it's a little bit more problematic, right? Because we're saying that our system is somehow inherently unstable. What we often will do is that we can say, okay, as a sort of a system designer, someone trying to analyze a particular scenario, maybe it's okay to allow for a little bit of instability. And this sort of gets back, I think, to your question, kind of, in that maybe it's okay, maybe it's difficult to switch groups. Okay? So maybe we've all formed groups, but to move to another table involves finding another chair and getting people to move aside, and that's just a real pain, and we can't be bothered to do that, even if we know it might lead to being at a nicer table. So we won't bother. And so we can capture this idea of, we'll have systems which are not stable, but in order to make changes and move to a different outcome, it's too much of a hassle. And so we can so we allow for this little bit of instability, so the gains from breaking away are really small. And so we have this notion of the epsilon core, which is simply the same kind of constraints that we had from defining the core, but now we allow for a little bit more flexibility, have some additional tolerance as to for these constraints. Now, for the epsilon core, if epsilon is 0, then we just recover this definition of the core. What's more interesting is to ask, if we do have an unstable cooperative game, how much instability do we have to allow? And there's a notion called the least core, which is simply the epsilon core, which has the smallest possible epsilon such that all these constraints are satisfied. And that can be kind of interesting to understand. How close to full stability do you have? Or potentially as maybe an outside designer, setting up an organization or a platform, how much extra incentives you might have to put into the system in order to remove these instability concerns. Yes?
What's the computational complexity to verify stability?
To verify, it's just setting, it's just checking those constraints. To compute it is a really, really hard, it's NP hard. Or worse, but we'll talk about some approximations just in a couple of slides. Okay. There are people, including myself and the collaborators, do have ways of computing sort of epsilon, so these least cores quickly at scale. But to find the core is, it's a hard problem. All these cooperative game theory concepts are almost always going to be difficult because what's the space you're working over? A set of all possible subsets of agents, right? So, of course, they're going to be difficult. Okay. So the other parts, that was sort of some of the basic ideas when we talk about stability. There are going to be other solution concepts which are related to stability. There's something called the nucleolus, and there's bargaining sets, and so on. They're really interesting. They tend to be a little bit more complicated, definitely to explain, and so I'm not going to talk about them here. The core and the least core are sort of the most common concepts that we have, but there are others out there. And again, depending on kind of your underlying application or what you're trying to achieve, they can be relevant. The other thing I wanted to talk about is stability. Is fairness. So the core addresses sort of stability. Something that's in the core, it might stabilize your system, but it doesn't necessarily, if you look at it objectively or an agent looks at it, they might not be happy still. They might say, okay, I'm stuck with this. I understand that I can't actually renegotiate this deal because nobody else is willing to negotiate with me and form another coalition, but it might not be fair. Right? And so when we talk about fairness, we want to know, well, do the payoffs or these credits that we're assigning to the agents as part of the group, are they somehow correctly capturing what that agent is actually contributing? So of course the question always is, what does it mean to be fair? And what's quite nice is that there's actually an axiomatic definition of fairness. So in cooperative game theory, when we talk about fairness, we almost always mean looking for symmetry. It says two agents who are interchangeable should receive an equal share. We have a dummy axiom. So an agent who always contributes the same amount as they would contribute independently should get that amount. So if somebody contributes nothing, they should get nothing. The idea? And then there's like an additivity axiom, which says, well, if we remodel the setting as two cooperative games, if payoffs somehow split between these games, then the agents should receive the sum of what they would get in the two games. It's a little bit complicated to actually formalize, to actually explain what's going on. But what is interesting is that there are other axiomatizations that replaces additivity assumption with a monotonicity assumption, and you still get sort of a similar result. So in particular, the Shapley value, which I'm sure most of you have heard about, is the unique payoff division that satisfies these three axioms. So in particular, if you think that these, symmetry, the dummy, and the additivity, or if we replace dummy and additivity from monotonicity axiom by Young, and you believe that this is somehow capturing fairness, then the result is that you have to be using the Shapley value. That's the only way of fairly dividing the value of the coalition among the agents. So what is the Shapley value? Again, I am going to assume most of you are familiar with this because it has it's been around for a long time, but also it's had a very recent adoption in explainable AI through SHAP and all its variants. Basically, the formula looks a little bit complicated, and it's definitely hard to compute because you're going through all possible permutations of agents and so on and so forth. But basically what it is that the Shapley value of a game, of an agent in a game, is just the average marginal contribution of an agent. Right? So it somehow does sort of make sense as something that you might want to share. In particular, that marginal contribution bit is that part at the end. So it's sort of the difference between the value of a coalition with agent I minus the value of the coalition that did not contain agent I. And then you're summing over all possible coalitions and all possible ways that coalition could have formed by agents joining over time. That's how you compute this average marginal contribution. So we can look here. Go back to my running examples. So we have the treasure game. Again, what's kind of nice about Shapley is because even though it's sort of a hard problem to compute, going again over all possible permutations, because it's axiomatic, sometimes you can compute it kind of like vibes-based. So if the treasure game, we have symmetric agents, no reason to distinguish one between the other, and so the Shapley value maintains that each agent gets an equal share. Okay. The voting game, again, is different. The agents, if we thought of the parties or sets of representatives as an individual agents, that first party A had a lot more representatives in it. They had 45 as opposed to, I think, 25 and 15 in the others. And so it somehow has a larger impact on outcomes. And when we compute sort of the Shapley value, we get this division. So that first party A gets 50. They get half of the value of the coalition. The other three, even though they had different numbers of representatives, all in some sense had the same sort of contribution or power, and so they split the rest between themselves equally. Sorry. Any questions about Shapley? No, this is stuff. Okay, so I have a little bit over 15 minutes, so I'll go a little bit beyond the basics. So in particular, I'm going to talk about 3 different lines of work in this space. 2 of them I've been involved in, the other one is not. The other one's just a model I really like and I think it's timely to revisit. So the first is approximating the core at scale. It's related to a question somebody had asked earlier about how hard is it to compute the core. It's hard. But there are ways of approximating the core. And so I'll just point you to a particular paper. Other people have also worked at this problem using different techniques. The second thing I'll talk about quite quickly is actually a paper that I've been very fond of. And that is going back and thinking about the Shapley value. In particular, is Shapley value really the right way to think about fairness? So Shapley is an axiomatic, based. It poses that these are the fair axioms. And so this is a unique value in order to support those axioms. But then the question becomes, well, are those axioms actually capturing something related to fairness? Particularly if we are designing systems where we want to work with people. And then finally, I'll talk about cooperative game representations. I've been particularly interested recently in this older paper on coalitional skill games. Right now, what I've talked about, the cooperative game definition, is very, very abstract. They ground it a little bit, try to one particular instance where you might have the forming of groups. It's kind of interesting, I think it's relevant, particularly for some of the recent agentic multi-agent systems that we're seeing appear these days. So the first thing, again, I don't have time to go into any details, so really this is just sort of pointing in a particular research question or an approach for trying to figure out whether we have in a large-scale cooperative game, whether we can actually stabilize it. In particular, does the core exist? So is there a stabilizing payoff vector that we can use to make sure that we have stability? Or if we don't, can we sort of figure out, well, what's the smallest epsilon, so what's the least core, so that we can have sort of only very small deviations, or we can maybe pump that into the system in order to stabilize. Okay. So in particular in this paper, I won't go into detail, we had a variety of different algorithms, but we showed that it is possible to scale up these core computations by using a variety of different approaches, including variants of stochastic gradient descent, by carefully defining a loss function, which is kind of capturing the deviation that some particular set of coalitions that you have you sampled in your batch is pretty close to satisfying the core constraints for that particular context and iterating. So you can formulate this as a stochastic gradient descent problem. So why is this potentially interesting? Well, as I say, it's interesting to know whether we can stabilize a system or not. But also, I could hypothesize, and this is something that Ariel Bracacia, who talked to you yesterday, has also been thinking about a little bit, is that cooperative game theory through the Shapley value has actually been highly influential in some of the explainable AI literature, which has been exciting to see, but also sometimes a little bit surprising because it's axiomatic and not all those axioms actually make sense and explainable in some of the context that's being used. But here's a different way of thinking about groups and contributions to, feature contributions, for example. And so it may form as a complement to the Shapley value-based approaches. And there are other settings also where the stability concepts are interesting, that we want to scale. The second thing, again, I've always liked this paper. The paper was testing axioms against human reward divisions in cooperative game. So in particular, what we did is that we went off and we said, okay, let's have these cooperative games. We told a little story about dividing, you're going off into the forest and collecting gold, for example. And we said, okay, how do you divide those rewards among the different players in the game? In particular, what would be fair? And we didn't tell people what fairness meant. We just said, you tell us what you think would be a fair outcome. And then what we did is that we tried to understand whether there was a relationship between the Shapley value and the human reward division that were being proposed. There's a broader context here. We had done earlier work trying to understand whether fairness actually matters. And yes, people care about fairness greatly. It was just unclear what they meant by fairness. And we narrowed in on the Shapley value, trying to compare about with fairness, human fairness concept with the Shapley value. What we found here is we have lots and lots of graphs that look like this. Those blue, the black dot in the middle was sort of an equal division of rewards. Those blue dots were the Shapley value. My student Greg Dion had been very clever in designing cooperative games so that we could fix a Shapley value, but have games that looked really, really different. What we found, though, that people didn't like the Shapley value. They didn't know what the Shapley value is, but they didn't like it, but they were actually quite consistent in what they thought was fair. So people were consistent in what they viewed fair outcomes should be, but it was not the Shapley value, it was something different. So then we went back and we said, okay, well, if it's not the Shapley value, they must be violating some axiom. So what axiom are they violating? Symmetry they didn't violate. We actually did sort of hypothesis testing, but whether the axioms were supported or not. People like symmetry. Dummy agent, they didn't like. In particular, there always seemed to be value in dummy, even if you contributed nothing, there was value in just being there and turning up. And that additivity axiom also was highly problematic. That was really causing major deviations away from the Shapley value. As I had mentioned earlier, there's alternative axiomatizations of the Shapley value. You can replace the dummy and additivity with a strong monotonicity property, which of course was also being violated in our data. But there were weakenings of the strong monotonicity property, sort of local and coalitional monotonicity, where actually our data was showing quite a bit of support for. So this was kind of an interesting paper for us in that we started trying to understand what it meant to do fair reward division. And it wasn't Shapley, but still it's something sort of seems to be highly structured. And relaxations of some of these properties might be lead to interesting new values. That's our hypothesis. Now, the last paper, again, I have citations, we won't talk, you should go off and read this, it's an interesting model, was this cooperative game representations, this computing cooperative solution concepts in what they call coalitional skill games. So most of the paper is talking about how do you compute Shapley, how do you compute the core, how do you compute the epsilon core for a particular class of games, but I think the class of games itself was quite interesting. The idea was that you study kind of collaboration and cooperation using abstract notions of tasks and skills. So an agent was endowed with some capabilities or some skills, and then there was a bunch of tasks. The tasks that need to be accomplished require different skills. Okay, and so then the question becomes, well, what can the agents work together and coordinate with their skill sets so that they can complete tasks? They can only complete a task if they have that right combination of skills or capabilities inside your coalition. And then they have your characteristic function. Well, it's some map that's from the set of tasks that agents could accomplish by working together into some real value, right? Again, quite a bit of flexibility how you actually instantiate that. Now, why I think this is interesting is that came across this paper as published this year, which talked about multi-agent systems and had the lovely title, Why Do Multi-Agent LLM Systems Fail? Okay. We read this in my research group. Rage read it. I think Ben, among some others, talked me down, but that's okay. But it was actually, in retrospect, it was actually quite an interesting paper. So what they did a big survey of sort of recent deployed multi-agentic systems. And they made the observation that they were not working very well. They were all failing in all sorts of interesting ways. If you have any background and you know sort of how the multi-agent systems research community has built over the last 25 or 30 years, it was very obvious as to, the results here were not surprising. There was a tendency just to have agents and then stick them together and hope for the best, and we know that doesn't work. It's coordination, cooperation is hard. But what I did think was interesting is that almost every single system that was surveyed and tested in this paper, and there was quite a lot of them, were actually examples of coalitional skill games, right? So they had tasks that needed to be accomplished. Agents had to work together in order to accomplish them. Agents had different capabilities, but they talked about these capabilities as tool calling or simulating roles and so on and so forth. But all of these mapped really quite elegantly into these coalitional skill games. So then the question becomes, well, does this quite abstract representation of cooperative structures, could that then, which does provide some insights as to what could be stabilized, what could be fair, and so on, could this then be applied to these sort of systems that we are seeing sort of deployed right now, or we might see deployed in the future, where we are trying to get this cooperation and collaboration between these sort of sets of agents with really different, very, very different capabilities. Okay, so I was going to have assigned, I have 5 minutes left, I was going to have you divide into groups, stable groups, and then talk among yourselves. We do stability here, not fairness. In particular, these were the discussion topics that I was going to have you talk about. The one that I'm most interested in are getting ideas about fairness and what does that mean and how should we be thinking about fairness as we look forward at sort of cooperative AI. But I don't have enough time. So maybe over coffee or over lunch, you can talk about this and then email me your ideas. But what I will do is now open up for any questions or comments that people might have in my last 5 minutes. I also would like to point out, again, if you want, this talk was really foundational. So all I wanted you to do was to be aware cooperative game theory exists. They have these abstract models and they ask interesting questions, but I clearly didn't have the time to go into any depth. So I have some papers that I think are interesting that I provide citations for in my slides, and then 2 really good resources for cooperative game theory are the Shoham and Leighton Brown book on multi-agent systems, and the Chakirakis, Elkin, and Woodrich book on computational aspects of cooperative game theory. These were both, all have sections, well, one has a chapter, one has an entire book on cooperative game theory, but written from the perspective of computer scientists and AI researchers. So it tends to be quite accessible, maybe more accessible than some of the pure game theory or economics literature, where you would also find some of these ideas. Okay, so thank you, and happy to answer any questions.
So should I bring some of the... So one question that was upvoted a lot on the Slido, or it's actually 2 questions that I will group together because they kind of go together, is like what real use cases of this research you're most excited about, and maybe relatedly, like what boundaries do you see to applying this theoretical framework in real world settings and applications? So,
excellent. That's the thing. Okay, what are the boundaries? So this is actually what I'm most excited by. These are abstract models, and this is actually more broader. So this is about cooperative game theory, but I think also any of the foundational work in the cooperative AI space is going to have the same caveats, and I think opens up some really exciting research possibilities. So these are, the cooperative game theory stuff, whether you transfer utility games or NTU games or some of the variations, there's different representations that you can use, are models. And they make lots and lots of assumptions, right? So let's go back and think about Shapley. Shapley is it's axiomatic. It is defined by a set of properties. And some of those properties, I mean, we're seeing this now in the explainable AI literature where they embrace Shapley. We're also seeing a similar problem in some of the alignment, the RLHF, the predominant RLHF models that are being deployed, in that there are properties and there are assumptions that are encoded by choosing this particular model or approach and incorporating it into our systems, which might not make sense in the applications that we're going for. Okay? So if we go back to this paper, again, I've always liked this work. Keep on meaning to follow up on it. We were saying, okay, we're going to have this cooperative scenario and people are working together. We had an initial paper in this space where we had people doing group tasks. They were doing, it was a kind of an HCI-ish like paper where groups of people were transcribing podcasts, right? And so it's a really hard task and you get a better outcome if you can have people have groups sort of doing the transcription at the same time. And we asked, okay, so what's fair? Do you care about fair payoffs depending on how much work you put into and how accurate we were. And people did care. They cared about being paid well, but they also really cared about that the distribution of the rewards was sort of fair. So they would get upset if they saw someone who had contributed a lot get underpaid. So this has now motivated this work sort of about trying to understand, well, Shapley as a way of thinking about fairness. And what we found is that, these axioms, this is our default model of fairness, but the axioms aren't actually capturing something that's necessarily the right properties when people think about fairness. So in RLHF, a lot of that work right now in the alignment space is underlying a Bradley-Terry model, which is kind of a convenient mathematical model, allows you to have rewards, but it doesn't actually capture, there's a bunch of implicit assumptions and properties in that. It doesn't actually capture problems when we have heterogeneous groups, right? So what I think is interesting, I'm getting to the point, is to look at some of these models, sort of conceptual ideas, and then go and test and figure out carefully what properties do we want, what properties are going to be holding us back, and what are alternative properties or structures that we might want to sort of have in our systems or might begin to appear when we sort of move up and look at scale. So I think that is independent of the cooperative game theory thing. It's a true problem in cooperative game theory, but I think more broadly is something I think is really, really interesting. Hard to do, but exciting research opportunities.
Cool. Yeah, another question here, which is a bit more specific to the talk, is what is the complexity of validating if an outcome is in the core? There are exponentially many inequalities to verify, so I would imagine.
I think it's NP hard. I think you can verify. Because your input space is, there's a little trick because your input space is pretty large. So it's going to be NP hard. Actually, now I'm backing down. Where's Vince? He's actually written some of this work. There are going to be cases where it's NP hard. I'll say that. But some of them might be harder. I think there's going to be assumptions on what your characteristic function looks like, which will allow you then to check whether the core is empty or not quickly. In particular, there are some characteristic functions where we know that the core exists and coincides with the Shapley value, but in the general case, I can never keep my complexity classes straight. So it's at least going to be in NP hard, but some cases might be worse. I know if you move to the NTU game, things become much worse because your space is more complicated. But yeah, I'm sorry, I'll have to email me and I'll look it up for you.
Yeah, I think that's perhaps like the last question we will have time for, but someone is asking, can you share some reasons presented in the paper, why do multi-agent LLM systems fail? Do you think it can be addressed by having update the value function?
Okay, this is a really interesting, has anyone read this paper? Okay, yeah, I know Ariel has read it yesterday. We also, because we had talked, he had read it before, and because we've talked about it several times. It's a really, really interesting paper. A lot of these systems, these agentic systems that they studied, were just creating different agents and kind of hoping for the best, that they would figure out among themselves how to cooperate and coordinate. And then things began, and so there was really a lot of them had very, very limited kind of what I'll call sort of institutional support around them that could allow for some form of reasoning, kind of more at a higher level to try to figure out how that cooperation coordination would work. There was very limited or no consideration of sort of credit assignment, which would actually be related to some of this cooperative game theory ideas as to what happens if if the group fails as opposed to the individual fails. So I thought what they were missing in at least in the failure cases that are outlined in the paper, it's an interesting paper because they say, oh, it's not just that these agentic, these agents were breaking down. That wasn't, it was more that the coordination between them was breaking down. But it sort of raised the importance that we need to think at a higher level than just at the agent level. We need to be thinking more at the group level. And a lot of these systems just are not doing that. So cooperative game theory might be one way of thinking about the group level, because it puts the group at the center.
Thank you so much. We are at our time. Another round of applause for...